All right, so this is right where we left off last time, showing how these expressions can be combined to make larger expressions. Here we're mixing numerical stuff. There's also like an arithmetic operator. We also have these comparison operators. We have Boolean operators. There's a lot of operators thrown in there. Now, in order for this to work, it has to be type correct, meaning I can't be comparing like 101 with like an operator or something. Like everything needs to be matched up. But there we go. And we can simplify this. Looks like I've got an extra space here. Yeah, I do. Well, does 101 equal 100? Well, that's false. And we also saw last time that we could actually kind of like short circuit this evaluation by saying, well, false and anything is false, so I don't even care what's over there. The answer is false. And we could do it that way. And then here's one. We've got true, or we've got is 14 greater than 0, or yada, yada, yada. And we can go through and start to simplify by evaluating the subparts. Work our way all the way down to true at the end. That would evaluate to true. But similar to the previous one, true or anything is what? True. So similarly to before, true or is that like annihilator operation or like case? True or whatever is going to be true. So I don't even care what's going over there. So I can like short circuit this evaluation. Now it was true for or and it's false for and though, right? So just be aware. But that's kind of neat. And do note that these were just examples here. If you find yourself in code writing expressions that look like this, you're probably doing something wrong. Like your expression should not look like this. Chances are something's not going right. You've worked down the wrong path. Like this is too much, right? So yeah, you're doing something wrong. Even if we have these long lists of conditions to check, there are ways to make it more manageable as well, where you can kind of do it in like pieces. Any questions about those comparison and Boolean operators, though? Cool. These are operators that you've actually been using your whole life. You just never really thought about them. All right, now, testing your code and type hints. So for those of you in lab yesterday, this is going to be a review. Writing code is obviously a part of your job if you're writing code. But the other half of the job is demonstrating that your code is correct, like convincing yourself and other people that it's correct. And you do that with tests. If you write a function without tests, you're not done. That is incomplete. You have to write your tests. So, yeah, once you write your function, you need to ensure it's correct. Once a function is written, we often call it a few times to see that it's doing what we expect. If you've been writing a function being like, okay, I'm done, moving on, you're doing it wrong. You should be running it to be like, is it working correctly? But we want to be a little bit more systematic than that. Because I know we've been sitting down and maybe you write a function in lab and then you call it a few times and you're like, yeah, it's working. But we want to be more systematic. What we want to do is we want our code to like verify itself. And that might sound like, whoa, how do we do that? It's stupid simple. But also, in addition to like demonstrating correctness when writing tests, when we write the tests, it helps us think about like what is correct and incorrect. What is the expected behavior of this function? What are the different cases this function might need to deal with? Are there any edge cases? And I'll talk about these things shortly. So writing tests, for now, at this point in the semester, we're going to be keeping it really simple. As we move on through the semester, we're going to move to like a more correct way to write tests. But for now, we're going to keep it simple for like a really nice strategy that's not going to scare anyone. And we're going to use a simple function to demonstrate how one would write tests. Now, if we are to consider how we could test the absolute value function, this is a function that Python gives us for free. And for those of you that don't remember, the absolute value returns a positive version of whatever integer you give it. So if you give it 7, it gives you back 7. if you gave it -8, it will give you back 8. Okay? That's how absolute value works. And we can call it with abs. So I could say like print abs of 66. It's 66. -66. It's 66. Basically, get rid of the negative if it's there. That's all the function does. But now look, if Python gave us this function, it's going to be correct. We don't need to test the absolute value function. I get that. But we're going to test the absolute value function for demonstration purposes. All right? It's also a simple function, so it's not going to be overwhelming to think about what are all the cases we should test. So how could we test it? Well, I would want to do what I just did. Like, okay, if I give it a negative number, it gives me the positive number. And if I give it the positive number, it'll give me the positive number, right? So I say we want to check the absolute value of a positive number being itself. If we give it a negative number, we need the positive version of itself. And I guess we could consider like an edge case could be like 0, right? Because 0 isn't really positive or negative, but the absolute value of 0 is just 0, right? So that could be like an edge case, we could call it. So maybe we should check that the absolute value of 0 is 0. And we can see that it is. And I just tested it, and we can visually see because I called the function, and I printed out the result, and I can check it with my brain. We can see that, right? But a way we could do it more systematically is I could say, okay, assert that the absolute ABS of like 4 is equal to 4. Now, okay, let's write them all. Of -7 equals 7. And then assert of 0 equals 0.
And what does assert mean?
Oh, 1 second. So these values, like the fact that I picked 4 and -7 and 0, I mean 0 I picked because it was 0. I picked -7 because I just needed a negative number. It didn't need to be 7. Don't think that 7 has any special meaning here. It's just -7. Similarly with 4. I could have done like this. It doesn't matter. All right? If I'm going to hit run, nothing. We'll see nothing. Ignore the assert for a second. This is just a function call with an immediate comparison operator afterwards. When I call this function better give me back 4. There's no special meaning to this other than what the code says. If I call this, it should give me back 4, which we saw, right? I did like print. If I go down here and I print of 4, it returns 4. So this should give me back 4 if the function's working correctly. So if I give it 4, I expect to see 4. Did it? That's what this is checking. If I give it -2,347, it better give me back 2,347. So this is the input, this is the expected output, but does the actual output match what I expect? That's the pattern here. And similarly with the 0, do I get back 0? Now assert is a keyword in Python. That assert expects a Boolean to follow. Now you'll know that a comparison operator will give you back a Boolean. This will either be a true statement or a false statement, right? There's nothing more to it than that. This gives me a true or false statement. And assert has to see true after. If it sees false, if that evaluates to false, and keep in mind too, it's not that assert needs an expression. Assert needs something that ultimately evaluates to a Boolean. It could be just the Boolean itself. But assert, like, let me show you. Assert true, well, this is kind of like a useless line of code. Assert true, nothing happens. Okay? Like, okay, what's the point? But if it's false, the program crashes. And now we go, oh, something was wrong. So if the program runs after our assert tests, and you're doing everything right, and it runs perfectly and you see nothing, you're good. But if it crashes, we're in trouble. And this is a good thing, because you don't want to be running broken code, because broken code can cause a lot of trouble. So we write assert to say, if any of these are not true, stop running. That's the idea. Now, let's say, for example, I'm going to just copy this. I wrote the function broken absolute value. I did this on purpose. Obviously, it's broken. We know it's broken, but it's for demonstration purposes. Also, you wouldn't want to write this. There already is an absolute value, right? But let's say I wrote broken absolute value. I give it x, and it just returns x. So now again, I know what broken absolute value is going to do, but let's pretend we thought it was absolute value. So if I think so, and also note that the order that we put these doesn't matter, right? So before I put the function call on the left-hand side and what I expected on the right-hand side, here I flipped them. It doesn't really matter, just be consistent. But here, if I if I were to call like broken absolute value, again, assuming it's working correctly, even though we know it's not, if I call this, I better get back a 5. If I call this, I better get back a 5. And if I call it with this, I better get back a 0. So if I hit run, going like, okay, I wrote my function, I wrote my tests, it's all good, I hit run, it crashes. And it even tells us where it crashed. It passed the first one, but like this one, this is what crashed it. So it even gives me information about like under what conditions did it break. Oh, it worked for the positive number, but it didn't work for the negative number. Interesting. So not only is this test telling you that it's correct or not, but it also helps you find where the issue is because you're systematically testing these things in a way where it helps you narrow down the problem. You see? Yeah? Again, I know this is not going to work. We know, but let's pretend it was we thought it was. So we would go and then fix it accordingly. Any questions about what we're seeing right here? I'm seeing like puzzled looks on faces, so it makes me think there are questions. Remember, if you have a question, ask now, because I don't want 20 people lining up to ask the same question after lecture. Just ask now. Do everyone a favor. So everyone's happy? Okay. All right. All right, so there we go. It breaks. So this is Python telling us that the assertion failed. So asserts are a great way to enforce that some condition is true in order for the code to run. If it's not true, it breaks. And if you're like, I don't want my code to break, yes, you do. If your code is not correct, you want it to break. Now, it's entirely possible that you've written your tests wrong. Maybe it's not the function. Like if I go here, and maybe I accidentally like did a typo, and I do this, it'll fail. Now, it didn't fail because like the function was wrong. It's just because like, oh, my test, if I give it a 6, I better get back a 6, right? Like my test could be incorrect. That's entirely possible too. So you got to be careful and methodical about your tests that you're writing. So let's go back to the square of sum example. All right, I'm just going to go here. I'm just going to copy. I'll go down here. And you can see here I've got my wonderful doc string describing how the function works along with the parameters and what it's going to return, right? Obviously, you're going to also use watch those things. There's the function. Now, here are a number of tests, right? Square of sum 0, 0, I should get back 0. If I give it 1, -1, I should get back 0. If I give it 5, 5, I should get 100, -5, -5, get 100. And then I do some funny thing down here that I'll talk about later, but this particular case is checking like with floats as well, okay? And so you'll see here, it's important to test a couple of cases, and you kind of want to catch as many like unique possibilities as possible within reason, right? So what am I doing? Well, I'm checking 0, I'm checking if they cancel each other out, 2 positives, 2 negatives, a negative and a positive, same number 0, right? You could argue like, well, you should do where maybe they're not the same number, Matt. That you're right, that makes sense too. Maybe I should, but whatever, I didn't hear. All right, and if I hit run though, it all passes. This is great, right? So these asserts are helping me understand. Note, writing good tests and thinking about all the cases that you should do is something that's a skill you need to develop. Don't expect to sit down and be like, I know all the cases. Just, it's a skill you need to develop. Just slow down, think, and write the tests. And it's a skill you'll develop over your career coding type thing. So don't worry too much about not being an expert at writing tests off the bat and thinking all the cases. But do write your tests and try to think of all the cases. That's the exercise. Now you'll notice this funny thing here. And we did talk about this before, but it was a little while ago without context, so it may not have stuck. The computers suck at dividing, or sorry, really, the computers suck at floating point numbers. They really do. And I'll show you an example. If I go down here and I say print 0.1 plus 0.2, we get that nonsense. The computers suck at it. It's because there's an infinite number of numbers, but we can only represent a discrete number of them, so the computer has to like take some shortcuts to represent different numbers. But at the end of the day, we can see we got a problem. In fact, if I were to go here and say, here, let's do that, and then I'll do like 0.1 plus 0.2 equals 0.3, right? Because you would look at this, like ignoring the fact that this is a computer for a second. Look, 0.1 plus 0.2 is equal to 0.3, right? Well, it's going to say false, right? Like, thanks, Python. And this isn't a Python issue. This is a computer issue. This really isn't Python's fault. So, like, well, okay, well, clearly that's a problem, right? It should be obvious that this is a problem because, yeah, that is 3, and it's telling me it's not. What gives? Here's the trick. Whenever comparing floats, never use equals. Never. Never use equals equals. Never check for equality. Never do it. Instead, what you want to do, I'll just copy this and go down here. What I'm going to do is I'm going to take what I give it, and I'm going to minus what I expect. I'm going to calculate the difference between what I get and what I expect. If they're equal, what should the difference be? 0. Everyone say 0. Come on, wake up. If your face is in your phone and you're not taking notes, what are you doing here? Come on, wake up. If the two things are equal, what should their difference be? 0. Okay. But the problem we have is like, floating point numbers. It's going to be close, but it won't be equal. So we take the difference between the things. In fact, we take the absolute difference because we don't want negatives to give us trouble. You take the absolute difference, and you check that the absolute difference is less than some arbitrarily small number, like 0.00001. Now, if you go this way, it'll be true. Even though the computer is like, well, okay, it wouldn't be right. If their difference is small enough, good enough. And this is the way we get around floating point precision, because floating point precision issues are going to be very small errors. And there we go. And that, well, why does this work? Well, look, if these were integers, I could say, is your difference like less than, or is your difference 0? Well, yeah, it would work. It would be fine, right? Now, we can't check for 0, but we could check for something really close to 0, where we say, well, they're so close that they might as well be the same. In fact, they might even supposed to be the same, but it's a floating point precision issue. Is that clear? If you have this is a tricky thing, so if you have questions, ask. All right. So, and you might say like, well, how small do you go? Well, whatever makes sense for what you're doing. Like if I go too small, we're going to lose like the value of this, where like if it's so small, it's not going to work, right? But how do I decide how small? Pick something that's reasonable. And if you're thinking like, well, how do I know what's reasonable? Usually in the context of what you're doing, I used this example like yesterday in lab. In the context of what you're doing, like if you're, let's say you're measuring like the time difference between things, right? It's a race, right? And you want to see who comes across the line first. Well, someone did come across the line first, But my measuring instrument, my camera, my speed camera, can only capture to a millisecond, right? So any difference beyond a millisecond, like I couldn't have captured anyways, right? So that precision doesn't matter. So if we're thinking like milliseconds, like, okay, let's go beyond a millisecond. Okay, yeah, good enough, right? Or maybe you're using a ruler, which has little millimeter ticks on it, right? So again, like you can't go anything maybe if you're crazy, you might be able to be like, this is closer to the one tick than the other tick on the millimeter on there, right? Maybe you can try to go a little bit more precise using a ruler, but you're not getting anywhere near here. So if the difference is beyond that small, it's the same. It's going to be the same. It doesn't matter. Okay? So that's what this is doing here. Let me scroll up. Is I'm taking the absolute difference between, here's the input, the function, and its parameters. Here's what I expect. Calculate the difference, and is the difference less than that, or 0.01 greater than that, right? That's how we do it. Never compare floats using equals equals. It's just a rule in programming. Do it at your own risk. Okay? Okay. All right, in the above example, square sum tested a number of times. Take notice, I'm not testing just arbitrary values. Like there was kind of like a systematic way. Yeah, so, okay, maybe if maybe I should have had a couple more tests in there too, even there's an argument for that. But what I had is probably fine. And you don't want, you also test while considering that, there's sanity, right? Like, I could write a function like this. Like, let's say you wrote the code and I wrote the tests for your code. And by the way, you can write tests for your code before you write your code. And if you're like, how? If I tell you, write a function to calculate the square root of the sum of two numbers, you don't need to write any code to go and pre-calculate what the square root of the sum of two numbers is, right? You can write your tests before you even write your function. Some people do that. It's called test-driven development. And I'm not saying it's necessarily a good idea, but it is something you could do. You don't need working code to write tests. Some people just like the tests to even kind of guide how the code would look and how it should operate. But yeah, what was I going to say? Okay, and when writing tests, you can assume sanity. We haven't learned this yet, but if I were to be okay, if A is 6, return 777, right? So if I were to write a test down here, okay, I'm testing 5 and 5, and I were to do 6, and it's oh no, it's not going to work or something, right? Oh, also it wouldn't be a 100, it would be whatever that is, right? So what's 11 squared? 110? I don't know. 121? And you're why isn't it working, right? You would assume sanity on the person writing the test. If it worked for -5, it's probably going to work for -4 and -4. There's no need to test -4 and -4. It's not reasonable to expect that it wouldn't work. And you could say, what if some asshole did this? That's on them, not on you. And by the way, let's say this is wrong, right? I just made the function wrong for the sake of argument. You will notice that it won't run all the tests. It runs them in order, and it crashes at the first one that doesn't work. So be aware of that. And you'll notice that when it crashes, it doesn't tell you anything other than it crashed. And if you're left, well, but how do I know? Okay, so why is it wrong? Don't worry, just print it out. So this one failed. Okay, copy what the function's doing, and then just print out, oh, it gave me a 1 and I expected a 0, right? So you would have to print out what it's giving you in order to see, did it work or not? And also, just make sure you put your prints above the assert, because if you put it below the assert that's failing, when it fails, the code stops running. It'll never run the print, right? So just put it ahead, that's all. Okay. Yeah, and this is me explaining that. Great. If my whole sufficiently small number thing, the absolute difference wasn't clear, just there's a description there. Yeah. Testing can feel like a lot more like an art than a science. Yeah, absolutely. Here's some tests for Celsius to Fahrenheit. And the point of what I'm showing you here is like, yeah, for every function, you really should be writing your tests. Always write your tests. If you wrote your test without any, if you wrote your function without any tests, you're not done. No one wants, if you get a job as a programmer and you submit code, like a pull request, and you don't write tests, they will viscerate you. Like, you write your tests. It's your job to write the test. No one's writing your test for you. If you wrote code, prove it to me empirically as best as you can with these systematic tests that it's working. Now, just because your function passes all the tests doesn't mean it's necessarily correct, but it should be a damn good indication that it's probably correct, right? Raise your hand if you've read through assignment 1. Okay, if you haven't, I recommend it, but you'll notice a bunch of assert tests in there that are commented out. Once you're done your function, uncomment them out and run them. If all the tests pass, you're probably right. You probably did the function right. If some of your tests fail, look at what it tells you. Why did it fail? It'll help you debug. It will give you pointers in the right direction. It won't solve your problems for you, but it'll help you understand and point you in the right direction. Also, I'll take it aside. Here's my advice. Like, raise your hand if you're first year. Okay, so listen. I'm going to give you advice on how to do all of your computer science assignments. I don't know how well this will work for other disciplines, but here's how you do computer science assignments. First of all, you need to recognize that writing the code is not, like, that's the last thing you do, okay? Step 1 is, what's the problem? Step 2 is, how could I solve this problem? Step 3 is, write the code to solve the problem. You have to do the first 2 things. If you sit down and start trying to type code, that's not gonna work. I don't even know why you think that'll work. It ain't gonna work. So here's my advice. When you get an assignment, as soon as it's released, read it. But don't expect to write any code for a while. Just read it. All your job right now is to understand it. Because understanding a problem might take a couple of days of just kind of like thinking about it. If you read your assignment at 8 p.m. and it's due at midnight, yeah, good luck. It ain't gonna work. So as soon as an assignment is released, read it, and then just think about it. If you have questions, ask me. If you read through it, what do you mean by that? Oh, I'll explain it. Easy peasy, right? But read it as soon as you're done, and don't expect to write a single line of code for at least a week or something. In the meantime, as you think about it and you understand it, when you're walking home, when you're in the shower, whatever, just, if I did that with like, okay, I could check you'll start to think of solutions whether you like it or not. Then, next thing you know, you'll have a solution, or at least what you think is a solution. Maybe it's not going to work, but you'll have an idea. Then you sit down, and then you write it. Also, another tip. One of the best things you can do, this might not make a lot of sense at this stage yet, but maybe on assignment 3 or something once we get far enough along, if you're writing code and you're stuck on a bug, which it's going to happen. If it's not happening, that doesn't make sense. Remember, programming is debugging. You're going to be right every time before you're wrong, so remember that. But sometimes you hit a bug where you've spent maybe literally hours going like, what? Like what? The best thing you can do is just stop. Beating your head against that keyboard for another hour is probably not going to do it. You just need to take a step back, and almost always the next morning I'm like, I know how to fix it. Like you will just kind of like figure it out. So don't dig yourself in too much of a hole. Anyways, yeah, the tests on the assignment, cool. All right, so here's some tests for Celsius to Fahrenheit, great. Notice the key broad tests, input of 0, -40, where they're the same, -5, 30, some floating point numbers, there we go. If you end up writing tests and you add a couple more that I could argue are unnecessary, it's fine. You're not hurting anybody. Okay, automated testing. Typically, like if you're a software engineer, you're not going to do your tests this way. but this is a fantastic way for this stage. It's a brilliant way for at our stage. Near the end of the semester, we're going to start using like the correct tools for testing. Specifically, we're going to use something called unit tests. We can't use it yet because we got to learn a little bit before it'll even make kind of sense, because it requires some knowledge that we'll get near the end of the semester. But at this stage, it's something more fancy is coming that has a little bit more bells and whistles. And we do need, like, there are limitations of this style of testing. For our needs right now, it's fantastic. But it's going to get to the point where things get a little hairy to test, where you need a little bit more sophisticated tools. So by the time that comes, we're going to switch to a different style of test for those. All right. Any questions about testing? Well, that's it for now for testing. Yes?
So I guess I'm trying to understand when you would do a test like that. Like when you have a function and you want to...
Yes.
Okay.
You only really test functions.
Okay.
You're like top level code. Like sure, these are the tests, but let's say I've got a bunch of code down here, blah, 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 and I call the function. That you wouldn't test. Like only like your functions you test.
Okay.
And if you're writing code well, like these lines of code here are going to be simple lines of code that are like basic arithmetic, blah, 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 blah. You hit run, does it look like it's working? You're good. It's the functions, those like units of like abstraction that do a bunch of stuff that you want to make sure are correct. And you don't need, like I showed you the absolute value example, don't test Python's functions. You don't need to test print, you don't need to test type, you don't need to test absolute value, like they're fine.
Okay. Thank you.
Yeah. All right, next, type hints. When you look at this method signature, def add together AB, what do you see? Well, this is a function called add together that takes it has two parameters. But here's the thing. In this particular case, it's kind of obvious, but there's going to be a lot of functions that are out there that you write, that you could use, that are in the standard library, where maybe it takes parameters, but like, what are the types of the arguments that I should give it, right? Let me show you here. Add together. I'm going to go here. I'm going to get rid of the docstring for fun. Right? And if I go here, I've used this example many times. I hit run. First number 1, second number 2, the answer is 12. Right? Right? Of course, we all know 1 plus 2 is 12, right? Of course not. Now, like, what happened here? Now, first and foremost, let me preface this with type hints won't actually fix this for you, but it helps hedge against this. It helps protect against it, but it won't actually solve any problems for you. What happened here? Look, this function, look, maybe this is what I wanted, maybe, but I'm going to guess like this probably wanted to like add them together, addition. Meaning that these should have been numbers. But what happened? I gave it strings. Okay? But I have no way of knowing that even just by looking at this. Right? I don't know. It just takes there's two parameters, A and B. What data type should they be? Because the behavior of this function is going to be very different depending on what the type of data is. Correct? 2 numbers, it gives me the sum. 2 strings, it gives me the concatenation. So there's like ambiguity. And the last thing you want in programming is ambiguity. That's bad. So what can we do? Well, in some programming languages, Python is what we call a dynamically typed language. Python does its best to figure out the types as it goes. And it's loosey-goosey with types. And you might think that's great, kind of terrible. There are other languages out there that are statically typed, where you must specify the type of everything. You would say something like int A and int B. And if I tried to run this, and okay, pause, If you're wondering, how come it was giving it strings? Remember, input always reads strings. If you want it to be an integer, you need to like turn it to an integer. But if I were to do something like this in a language like Java, which we'll be using next semester, and I tried to call the function with the string 1 and the string 2, Java wouldn't even run the code. It's not that it would run and crash. Java would say, no, 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 no. Your function's supposed to take integers, and you gave it strings, thereby not even allowing you to make this mistake. I mean, you could make it, but it would force you to fix it before you could even run the code. Now, Python is not that strict, but we have something called type hints. And the type hints, they're not for Python, they're for programmers. It's kind of like a way to encode comments, a description of how this code is to be used, into the code itself. And that's a good thing. You want your code to be self-descriptive. So we use type hints. And I would say, okay, A is, let's say this will work with floats. Float. Float. So this would mean this function expects two parameters, A and B, that are both floats. We also like to say, because this function returns something. What does it return? A float. So what this syntax means is, add together, takes two parameters, they should both be floats, and it's going to give you back a float. So, like, what will be in result after? Well, it should be a float. Well, I don't know what float it is, but it should be a float. Why? Well, because this function is supposed to give me a float back. This is a way to encode into your code more information to programmers, to yourself, because you'll always forget your function, like what they do later. It always happens. And if I give this code to someone else, they would look at this and be like, oh, it's two floats. Like, they know. There's no mystery. It's there. But Python will not enforce anything. You can misuse it, and Python will let you misuse this. For example, 3 and 6, it'll still give me back 36. It expected a float, it was going to give you back a float. I was still able to give it a string, another string, and it gave me back a string. So Python will not enforce this, but it's a way to make your code more reflective and descriptive. So, in addition to always writing your doc strings for your functions, always, 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 which I deleted mine here, in addition to always writing your assert tests, which I didn't bother here, always include your type hints. That is a way to make your code good. So you want your doc strings, your type hints, and your tests. Always write those. No type hints, so there you go, right? Also, you can say, like, you can add these to your doc strings. Some people like to do this, like R type, that's the return type. Actually, if I were to do this, I'd probably put it above the return. But R type is a float, right? So it's in the doc string. Though a lot of people would say, you really don't need it. It's return type is a float because it says it right here. This would be like what you did if you didn't use type hints, maybe, like a way to describe. But in general, use type hints. If you like to add these things to your doc strings with all the types, by all means, go for it. But you really don't need to. Yeah. So what you get. Oh, yeah, another thing, too. Yeah. Check this out, right? Like, when I go down here, because Python loves, like, okay, hold on. Stop. I'm going to add this back in. Yeah, man, the indentation's all wild. Okay, cool. Okay, stop. So let's say I go down here, and just for whatever reason, I'm going to call add together. So, look. Check this out. This is cool, right? This is Colab. Like, I'm calling this function, right? This could be like a billion lines. This could be somewhere way else inside the code, and I'm calling this function. And look what it's doing. Well, add together A. It expects a float. expect it'll give you back a float. And it actually, like, this is the doc string right there. Look at that. It's pretty cool, right? Because if we follow all the format correctly, it's going to be able to kind of like do these nice things for us. And I'm just getting this, like I typed it in, I hover over, and it just tells me. And another thing too, like add together, you can even see like in this autocomplete. By the way, if you ever see this autocomplete and you're like, yeah, that's what I want, just press tab. It'll go, it's pretty nice. It also tells you like there too, right? It's pretty cool. Yeah, what you get, what you don't get, it'll still let you shoot yourself in the foot with mixing and maxing type, blah, 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 messing up your types. Any questions about type hints? It doesn't make Python do anything for you. All it allows is for more expressive code, which we like. We love that. Code is not for computers. It's for humans. Contrary to what you've been told all this time, bytecode and machine code is for computers. Like zeros and ones are for computers. Code is not. Yeah?
For the typings, is it like extremely strict on like the formatting of it?
Yes.
Okay.
Like, they need to be like colons here. And then this little like, it's like, it's an arrow. It's minus greater than, you know. Like this is just a minus symbol and that's a greater than symbol, but this looks like a cute little arrow, right? That's what it's telling you. Like it gives you back a float. All right. Yeah. There do exist things called like static type checkers for Python where if you do all this, you can run another piece of software that will go and check it all before you run your code for you, which is kind of neat, but we're not using that. It's not part of like Python. It's like another thing people have tacked on. The fact that types aren't, like Python's types are dynamic and not static is probably one of the #1 things programmers dislike about Python. That's like my least favorite thing about it. The number of errors that I have dealt with that are a consequence of just the language being dynamically typed have caused where like if I was doing the same thing in another language where it was statically typed, I would like the error could never have happened in the first place, which is nice. So a lot of times, like next semester we move to Java, people get all weirded out. Oh, it's a different language, it's harder, Java's scary. Java forces you to write code in a way that will never allow you to make certain bugs and mistakes that you can do all day in Python. So it's actually really awesome. But I do find Python is probably the best language for like, let's start learning the operations and things in coding. So I'm really not hating on Python. I love it. Of all the languages I use Python far and away the most of the time, right? And I said this in lab yesterday. There's languages everybody hates and languages no one uses, right? So everyone hates every language, but those are the ones that you use. All of the good languages no one uses because they're not actually good. We just like to complain a lot, right? All right. If else. Now, look, I say this is an activity, but we're not going to do it because of the sake of time. We'll do it together. I'm saying, okay, write a function called smush a number right? Okay, let's add let's call it a float, and it'll give you back. Well, let's read what it is. Smush a number that checks if the number is positive or negative. If a number is positive, the function will return half the value of a number. If it's not positive, just return a number. Okay, what does that mean? Well, if it's a positive number, like if I gave it 10, it should give me back 5. If I gave it negative 10, it would give me back negative 10. Simple function. What is its utility? Nothing beyond serving as an example. Okay, so it'll give me back a float. All right, let's pretend there's a doc string here. Okay, now how do I do this? All right, so if the number is positive, I need half of it. Well, I can check if a number is positive. If a number is like greater than 0. But like how, like I've got a problem. I can check this, because this will either be true or false, right? In fact, let's just, for testing purposes, by the way, prints should be your best friend for testing. I know I say like never put prints in a function. When you're writing and testing a function, by all means throw prints in there all you want. Just when you're done and what you want to do, just get rid of the prints. You don't want them there. But just for the sake of testing and just playing around, let's see, like smush 10. It's true, but like negative 10, false. 0 is false, but I guess like that doesn't really matter because half of 0 is 0, and 0 is also 0, so that part doesn't matter. So I can check. I can get a Boolean that'll tell me whether it's a positive or negative effectively, right? That's what this is checking. Is the number positive? Is the number negative? But the issue I'm faced with is I have to do two different things depending on what this is. Do you see? If a number is greater than 0, true, I need to return half of a number. If this is not the case, if it's negative, I just return a number. So I have to like go down here, I hit this point and I have a question to ask. And then depending on the answer to that question, I want to do one of two things. But I currently don't have a way to do that. I don't have a way to like branch, to do one thing or another thing. All of our code has run one line at a time, one after the other. How on earth, like what do I do? So the activity is, well, write the function to do that. The catch is, we can't. I mean, we can, we just need to learn how. And it's with something called conditional expressions, if statements, where we effectively, what we say is, if this is true, do one thing, otherwise something else, for example. It allows for branching. So this is where we can say like if else, do this, do that. It allows us to branch. That's what it is. And these ifs require a Boolean. Not a Boolean expression. It needs something that evaluates to a Boolean. It could be a Boolean, a literal Boolean, or an expression that evaluates to a Boolean, but the point is it needs something that's either going to be true or false. All right, so Booleans were discussed. They're a type. We saw like Boolean operations, comparison operators, like Booleans. We'll take two Booleans, give you a Boolean. Comparison operators will give you like, you could compare numbers and it gives you a Boolean. But Booleans allow for more than just true, false. I mean, ultimately they do allow for just true, false, but then we use Booleans in a way to help us make decisions, like basically how we could address the smush problem. So we know how we can ask if a number is positive. Is it greater than 0? Right? Someone here could be like, what about greater than or equal to 0? Fine. It's not going to matter for the functionality of the program. I don't want to get into the philosophy of 0. That doesn't matter. But the key is now we need to tell Python that if some condition is true, do something. So have a look at this code. Return value is a number, but if a number is greater than 0, return value will actually be half of a number. Return value. This code will only run if that condition is true. Or more specifically in this case, this code will only run if a number is a positive integer. Otherwise, this gets skipped entirely, meaning return value is left alone. We'll pick up here on Tuesday, though.